All right, so here we are again. Now, today what we're going to do is wrap up chapter one. This set of slides I'm showing you right here is actually section 1D. That's the end of the chapter. And so when we're done with that, we'll dive into chapter two, and then we'll be ready to have our first assignment. Now, chapter two is a look at applications of integration taken from the real world. Many of them are from physics, but we'll see if there's others as well. And but for here, we're going to carry on with our discussion about integration of logarithmic and exponential functions. And as always, the more practice, the better. So the more of these examples we look at, the better off we'll be, because there's so many different interesting cases that can show up. Now, when we look at something like this one, our first instinct is to look at it and say, wow, that looks really scary. But often our first strategy, no matter what type of problem we're working on, is to see if we can simplify it and then reduce it to something which we can recognize what we're supposed to do with it. So why don't we do this? Let's rewrite this slightly. In the 4 outside, I think bringing the constant outside is a good idea because it helps us, it reduces the complexity of the expression. Then we have e to the x to the minus 2 power. Now, this x cubed, since it's in the denominator, of course, is equal to x to the minus 3 power. So now what we're going to do is look for a definition for u. And of course, when we choose u, we have to understand that we also need a dx, a du rather. And so let's think about this. Look at this exponent, x to the minus second power. Now, you know that when you differentiate x to the n power, we're going to end up with x to the minus 1. Sorry, n. Let me try that again. Hold on a second. Nx to the n minus 1 power. So how does that help us here? Because whatever we choose for u, du, well, we have to take into account this power rule. So let's say we choose u to be this exponent. Right? Then du dx is going to be minus 2 x to the minus 3 power, based on our power rule. Do we have that in our expression? Well, no, but we have x to the minus third power. That's the important part. We can't supply that ourselves, but we're missing the negative 2, but we can take care of that very easily by both multiplying this entire expression by negative 2 and then multiplying it by negative 1/2, so that we end up with a product of 1, which doesn't affect our results. So let's do that right now. I'll multiply the entire expression by negative 1/2. So that I can now multiply this expression by negative 2 without affecting our expression. Okay, so nothing's changed. I've just rewritten it in a slightly more convenient format. Okay, now let me just move this to the next slide and let's see how that helps us. Yeah, sometimes it'll let me oh, I got lucky. Sometimes it lets me copy the whole thing, and sometimes it's just I don't think there's any rhyme or reason to it. But all right, anyway, here's what we have. So what I'm noticing here is that if u, as we've already seen, u is x to the minus 2 power, which means that du dx is minus 2x to the minus 3, or du is minus 2x cubed dx. That's what we have here. Over here, we have e to the u. So when we multiply the negative 1/2 by 4, we have negative 2 e to the u du. Okay. And we know that that's equal to e to the u, evaluated from 1 to 2. And of course, u itself is x to the minus 2. So now this is reduced to some substitution. We have to be really careful here because you've got e raised to the 2 raised to the minus 2 power. And over here you have e raised to the 1 raised to the minus 2 power. Okay, because what you're replacing the x here with 2. This is where we used to have x, and here with 1. Okay, but remember the original expression was e to the x to the minus 2 power. So you've got minus 2. So 2 raised to the minus 4th power is e. So what we could do here, maybe to simplify this, is rewrite this as 1 over 2 to the positive 2 power. You don't have to do it that way, but I think it might be easier because, for example, that in general, so therefore, e to the 2 minus 2 must be e to the, okay. So therefore, what we have is e to the 1/4 minus e to the 1. And, you can distribute the minus 2 here if you need to or want to. You don't absolutely have to. And since this is e to the first, we can just write it as 2 to e. So it's still a messy problem. It's just that the way we cleaned it up, so to speak, that made it a little bit simpler. In other words, by moving out the 4 and then looking carefully at the exponent of e and remembering the power rule, what we realize is that choosing u equals e to the to x minus 2 is probably the way to go. If we had chosen, for example, x to the minus 3rd power as u, we would have discovered that we don't have what we need for the du. You would have needed some expression in terms of x to the minus 4th, and we just don't have that. All right, well, this one is definitely a bit of a challenge. And there's a lot of opportunities to make mistakes. So we have to be extra careful with these cases. Now, logs. All right. So here's some basic rules that we want to remember. These are things that you don't have to memorize them, but I think it might be a good idea because you'll run into these, and it really will make things simpler for you if you have memorized them. So, for example, the integral of 1 over x dx is the log of the absolute value of x plus the constant. Sometimes you see this as simply dx over x. Log x is x minus log x minus x plus c. It's a little bit messier. Now, this third one is just a special case of, or actually, I should say the second one is a special case of the third one, because what's actually happening here is that this a is e in this case. Remember that log, natural log, of x is really the same thing as log base e of x. And also, the natural log of e is just 1. So that's why this term doesn't appear up here, because it's just equal to 1. So the second expression is actually a special case of the third one. All right, so let's put to some good use. For example, what about this disaster? We might look at this and say, what are we supposed to do with this? All right, now remember, as a rule of thumb, we try to let u always be the messiest part of any expression. Usually that works out for the best, okay? Because remember, we need that du, and so let's start with u equals x to the x minus 10. Okay, we do have the dx, so let's get that 3 out of there. Okay, now we can rewrite this as and that means it's the log absolute c plus c. Okay, and so that's what this one is all about. So there's you're trying to get it into that form. Du over u is the natural log. Okay, once you recognize that, once you get good at this, you'll start to recognize these forms, and you'll see that, with a little rearrangement and the right choice of u, we can reduce this to something manageable. Oh, I just realized. Oh, yeah. I got very careless here. I left out the 3. You don't have to bother multiplying the 3 by the constant, by the way. It's just a constant. We don't know what it is anyway. So, but you do need the 3 here. Sorry about that. It's 3 log absolute x minus 10 plus c. All right. How about this one? Well, this looks pretty simple, but you know what? It doesn't appear to take any form that we're aware of. So why don't we try this? U equals x plus 2 du dx is just 1. So it looks very similar to the one we just did. ln u absolutely that is plus c. And so therefore that would be ln absolute x plus 2 plus c. And that's it, you're done. Okay. And that, yeah, that's all there is to it. Wow. All right, now here's some more interesting cases. Finding the integral of a rational function, which we discussed the other day. A rational function simply means that the function is itself a ratio of 2 other functions. So, for example, let's take a look at this one. Now, what are we supposed to do with that one? Well, one possibility is to write it like this. All to the minus 1 power, that is. So here's what we're going to do. Why don't we let u be this piece right here? Then du dx would be 4x cubed plus 6x. Du is 4x cubed plus 6x dx. Do we have that? No, but we're pretty close to having it, because if we multiply this expression by 2 and combine it with this dx, we will have what we need. So first, let's rewrite this slightly. And then what I'm going to do is multiply, as I've done so many times before, it outside by 1/2. And then here I'm going to multiply this by 2. So that what we end up with Ah, there we go. So let me just rewrite it slightly. Remember, we define u to be x to the fourth plus 3x squared, and du is 4x cubed plus 6x dx. So what do we have here? We've got 1/2 u to the minus 1 power times du. Now, of course, u to the minus 1 power is just another way of saying du over u. So you're going to have 1/2 natural log absolute u plus c. And of course, u was defined as x to the fourth plus 3x squared plus c. All right, so I just barely fit it in there, but you can see it's 1/2 log u plus c. The constant, I can leave it inside the parentheses or not. It doesn't really matter. It's understood that since this is an indefinite integral, that there'll be a constant of integration somewhere. It doesn't really matter what it is. Unless, now, if you really need that number, by the way, depending on the application, you can solve for that, but you need to be given one more piece of information. So in other words, if you're doing some applied problem where you must have that constant, you'll need to be provided with one more piece of data that will give you the specific value of c. Okay, but for our purposes right here, we don't need that. Now here's one. Look, I'm just going to give you a hint with this one. Let's go back to some of these earlier definitions. This one. Okay, actually, well, maybe I'll grab them both. Just as a quick reminder, now if you've done enough of these, you don't have to make a conscious effort to memorize them. You'll have it memorized, whether you realize it or not. So basically, you can see that a is equal to 2. Oh, well, that's easy then, because all we need is x over log 2 times log x minus 1 plus c. It seems to be getting a little slow there. Okay, that's it, because we recognize very cleverly that this one is just this special case that we saw earlier where a is equal to 2. All we do is literally replace the a with a 2 and we're all set. Yeah, I mean, that's it. That's literally all you had to do. Sometimes we get lucky. Sometimes it falls into a basic form. In fact, if you look at that table in the book, you'll see that this one will be there somewhere. And so sometimes if you're not sure what to do, you can just go through the list and see if there's any that look like they're similar to the problem that you have. And then maybe you can rearrange your equation algebraically and come up with the one that is right on the chart. All right, now here's one that might be a bit of a headache. Just a quick reminder, I think we discussed this the other day, just in case. The trig derivatives. There's a few that will be very, very helpful. These two in particular. Now, I'm sure the book has a chart of these. In fact, why don't we go get it and look at the chart? Let me go find the book. I'd be very surprised if there isn't a table in there. At the very least, there'll be a separate table for the trig derivatives and integrals. Because it's, it's a kind of thing that it takes time to remember. You can't be expected to memorize these that quickly. There, table of derivatives right there. Okay, so we've got all these standard ones that you know. There's the power rule that we've been using today. The trig functions, there you go. So the derivative of sine x is cosine x. The derivative of cosine x is negative sine x. And some of these others you may not need as often. The derivative of the tangent is secant squared, etc. So here they are. The inverse trig functions are log functions, the ones we've been looking at here. Hyperbolics, we may not need those for this class. But just be aware that they exist. Man, they're really being helpful here. Look at some of these extra goodies they're giving us. Geometry, the quadratic formula, et cetera, et cetera. Trig definitions. I like this book. Man, there's a lot of them. All right. Let's get back to this. So in other words, yes, that means we have to carefully choose the u that we want. So, and remember the rule of thumb is usually pick the more complicated function or component of the formula to let you to be your u. So let's try u equals 1 plus cosine x. Du dx would be negative sine x. Because of course the derivative of the 1 would just be 0. Now, do we have this? No, but we only need that negative. So we can rewrite this as negative integral from 0 to pi over 2, negative sine x dx over 1 plus cosine x. And so what we actually have here is du over u, which means that we're going to have a log of a trig function. All right, so once again, we got ourselves to this point. This one is a definite integral, so we don't have a constant. And u, of course, we chose it to be 1 plus cosine x. Okay, so the first thing we need to do is go figure out the cosine of pi over 2. You can do that on your Texas Instruments calculators if you want. I'm going to just pop open Symbolab. So cosine pi over 2 0. Okay. And the cosine of 0 is 1. Okay. Now, it just so happens the natural or any log of 1 is 0. Okay. So the fact that it's ln1, it doesn't matter what the base is. This first term is just 0. So that's going to be your final answer. Negative log 2. Oh, no, that's right. You know what I just realized? We forgot about the absolute value signs. I don't think that'll matter in this case. Because, yeah, these are both positive numbers. Oh, but you know what's missing? There was a negative here. The one that we supplied. All right. All right, let's get that out here. Yeah, I knew something was wrong. Yeah, because remember when we rewrote this, we needed that negative there. So it's actually positive log 2. There we go. All right, now we're good. Okay. All right, so remember up here, u equals 1. We need to supply the negative. So yeah, when I copied it, I missed this negative sign. So here it is now. Yeah, I got to watch it here. It's very different than writing on a whiteboard, that's for sure, because there's so little information on each slide. I have to keep going back and forth, but we're good now. Now, here's where it gets interesting. Remember, we looked at this chart a couple of other times. And some of these definitions, if you look at let's go back to the book for a minute and not look at the chart of derivatives, but of integrals. There's a handful of them. You might remember, oh, where's it? There it is. Okay, there's a handful of them. And you can see the list is very, very long. Wow, look at that list. Ooh, this is, yeah, that's why we don't memorize them. But in the list of the very basic ones, here we are. These last 3 all involve the inverse sine, the inverse tangent, and the inverse secant. Okay. So what exactly does that mean? So this one is pronounced arcsine, arctangent, and arcsecant, although they are inverses. What does that even mean? Well, for example, so, let me just look up one real fast in Symbolab. So, all right, this will do. The cosine of 0 is 1. That implies that the arc cosine of 1 is 0. So they're just basically the reverse of each other. Okay. The reason why the notation is to the -1 power is because they really are inverses. Okay, you're just taking the opposite. In other words, instead of having the 0, taking 0 and defining its cosine, what you're saying here is what value has a cosine of 1. Okay, so they're written as sine, arcsine, arccosine, and arctangent. But it just so happens that in 3 cases from our list of formulas, these last 3, and they look like very straightforward cases. In this case, you'll get an arcsine, In this case, you get an arctangent, and in this case, you get an arcsecant. But you have to recognize that form when you see it. So you can see that, like I said once before, the big challenge with these integrals is recognizing which form you're looking at, and then trying to figure out what technique to use. If you happen to find one of these standard ones that come right off the table, well, then you're all set. Like these, for example, suppose you ran into something like this. Oh, I have a list right here. Okay. What if I had this one? Now, if you look at the list, it looks like it's this first one because one is a constant. So according to the book, if you have du over radical a squared minus u squared, you're going to wind up with the arcsine of u over a. Plus c, of course, if it's an indefinite integral. So that's what we have here, with the understanding that a is simply equal to 1, and u is simply equal to x. Why? X, because it's u squared, if you notice in the formula. And that's important because then du dx is 1, or du equals dx. Okay, because otherwise we're not going to have what we need. So that means we have du in the numerator. 1 squared is just 1. X squared is x squared. So we have the arcsine of u over a. Now this one is evaluated between 0 and 1/2. But remember, u is, in our case, x, and a is just 1. Okay, so we're going to evaluate this. Let me repeat that here. Sine x, sorry, arcsine x, evaluated from 0 to 1/2. So now we can just go back to Symbolab and look these up, or else you can go to your calculator. Actually, oh, I happen to have mine right here. If you're used to using the TI-84, let's see, where are they? I'm looking at this. Oh, here they are. They're directly above the trig functions. In other words, if you look in your calculator, 2 rows up from 7, 8, and 9, you'll find the trig functions. And directly above those, the second functions are the arc functions. Let's see. So I'm trying it out right now. So what we should probably do here. Oh, by the way, these are supposed to be radians. So let's switch over on our calculator. I guess you don't have to do it in radians, but I think it'll be easier. Let's switch the mode to radians. And then try arcsine of 0.5. And like 0.5 something. Okay. Oh, I see what's happening. You see, the thing is, the calculator is giving me the decimal. Let's do this in Symbolab. Because usually these results are, when we're dealing with radians, these results are written in terms of pi. So let's see how Symbolab handles that. I don't think it will be any different than the calculator. Also, I'm not sure where they, wow. I'll have to look in Google to see how they implement arc signs. Okay, I guess the computer is upset with me. I think it's because I have too many windows open. Yeah. Um, no, it's just having a rough day. Yeah. Um, I don't know. I've never seen it act like this before. Well, I'll tell you what. I just happen to have another computer right over here. Hold on 1 second. I'm going to go to Symbolab on my other computer, which seems to not be working either for some reason. I tell you what, a day doesn't go by when the technology doesn't let me down. I can tell you that much. And here we go again. It's just unbelievable. It just doesn't feel like working. How about that? All right. Um, give this piece of crap another chance. Oh, it's awake now. Isn't that thoughtful? All right. So what I wanted to do is the arc sign, but oh, that's right. I forgot to look up. I'll tell you what, I'll look that up on my phone. I don't want to upset my computer. Oh, I see. All right. They want us to spell it out. Okay, that was the holdup. All right, I wasn't sure about that. All right, let's do that. Yes. Okay. Now this is good to see. They are actually giving us the value as a function of pi. Okay. The calculator, I don't know if it's possible for this calculator to do that. Um, there might be a setting in here somewhere, but if there is, I'm not aware of it. It comes up on my calculator as the actual decimal value of this, which is approximately 0.523598. Okay. But I'll tell you what, let's just leave it as pi over 6. Okay, so this term is pi over 6. Now, the arc sine of 0 turns out to be 0. Okay, so that's helpful. In fact, why don't we do this? Why don't we look at a graph of sine of x? So it's 0. Yeah, it's 0. And at 1/2, which is right about here. No, that's not right. It's right about, oh, it's over here somewhere. It's hard to tell by looking at this graph. But see, the sine of pi over 2, which is 90 degrees, is 1, but 1/2 is sort of in here somewhere. So, oh, look at this. You know what? I think that's it right there, because pi over 6 is approximately 0.52. Okay, so that confirms that what we've done is correct. So this our arc sine of 0 is 0. And we have pi over 6. That, at long last, is our final answer. Let's see. So let's go back. Yeah, so we don't need a constant. And so that's our final result. Very good. Now, what about this one? Now, remember, we had, if you look at our list from the book, any integral in the form du over radical a squared minus u squared equals, as we just saw, the arc sine, rather, of u over a plus c. Do we have that here? All right, let's find out. Let's let u be 3x. U squared would be 9x squared. Du dx would be 3. And then du would be 3 dx. A in this case could be just 2, because then, of course, a squared would be 4. So we're missing the 3, but that's not a problem. We can write this in the following way. And now it appears that we have what we're looking for, because that numerator is du. Oh, the numerator is du. The denominator is radical a squared minus u squared. Ah, so that's pretty straightforward. So I'll just repeat that right here. 1/3 arc sine u over a plus c. Now remember, we defined u as 3x and a is 2. And it is a definite integral. And that should be it. All right. Now, here's another one that looks, oh, let me leave it up there for a second so you can see it. Oh, so this time, oh, man. So what comes next? All right, let's see this next one. Now, if you notice this one, it looks superficially similar to the ones we just did, but instead of a squared minus u squared, we have something different, and there's no square root here either. What's going on with that one? Is that one of ours? Oh, now here's a candidate. It turns out integral of du over a squared plus u squared. Notice the lack of square root equals 1 over a arctan of u over a plus c. So it looks like that's the one that we're dealing with here. Now, by the way, if you didn't recognize this, if you started out and said, well, let's just let u be 1 plus 4x squared, you would have said, uh-oh, I need 8x. See, now I don't have an x or an 8. If I just was missing the 8, I'd be fine. But I can't just supply my own x, okay? Only constants. So that means that would have been the wrong way to go. And then I would have had to say, listen, what form does this thing take? Let me look at my list in the book and see if one of these fits. If not, I have to try something different. But of course, if so, you might as well take advantage of it. So here then, it should be clear that u would be the 1. I'm sorry, a is 1. A is the constant. U is the variable. That's going to be 2x because u squared then is 4x squared. And then furthermore, du dx is 2, so that du is 2 dx. Now, I don't have the 2. Oh, but that's not a problem, is it? No, I can always supply any constant that I need. So what I've got here is du over a squared plus u squared. So therefore, my answer is a of 1 over a arctan, arctan u over a plus c. But don't forget the 1/2. And then you'll have, now 1 is 1. I mean, sorry, a is 1, so this is just the arctan. And then u over a would just be 2x. And then we just have the constant here. Okay. Oh, wow. So that one, we were able to get that one because we recognized the form that it takes. All right. It just so happened to be one of our special cases that is listed in the back of this book. Now, later on in chapter 2, I think, you see how here's a separate list of trig integrals. This is a little different because you're integrating the actual trig functions directly. You see over here, you're not. The result is an arc sine or an arctan or an arcsecant, but you're not actually integrating the trig functions. Here you are. And so you can see there's a huge list of them. And some of them, God, look at some of these. Oh my God. Yeah, anytime trig functions get involved, the results can get very, very messy. And then here we're actually directly integrating the inverse trig functions or the arc sine, et cetera, et cetera. Okay, well, anyway, so we're actually done right now with chapter 1. So we're going to take a peek at chapter 2, which is our look. It's an overview of applications of this material. Here we're just learning the rules, and even then, just some of the rules, because in chapter 3, we're going to really go to town with integration functions. I mean, so far we've really only done a few cases, mostly involving substitution. We use substitution, I mean. In chapter 3, we'll be looking at a whole slew of rules and techniques that you'll be using for other cases. So let's at least open up chapter 2 and take a quick look at it. So we're going to be focusing our attention on applications. Now, some of these involve geometry, some of these involve physics, but they all are directly related to what we've been doing. Now, you might recall that we demonstrated that if you have some function or other and you're interested in knowing the area between two endpoints, if you notice here, we implicitly are assuming that the bottom of this shaded region is the x-axis. Okay, so all of those results we derived were based on the assumption that they're bounded from below by the x-axis. Okay, so in other words, the fundamental theorem of calculus tells us that if we're integrating between 2 points under a function with the bottom being the horizontal axis, then we can just directly integrate. But what if that's not true? What if we have 2 functions, not just some function and the x-axis, but let's say we have 2 functions, like here's f of x and here's g of x. You notice neither one of them is on the x-axis. So the shaded region, what do? How do I figure out the area using integration, given that I don't have the x-axis on the bottom? Well, it's a very straightforward extension of what we've been doing. What you're going to do is integrate between the 2 curves. You're going to take whichever one is the one on top. Now, the one on top is a very informal way of expressing the idea that no matter what x is, f of x is always at least as great as g of x. If that's the case, then f of x is the so-called top function and g of x is the so-called bottom function. If not, then it's the other way around. We always have the top minus the bottom. Otherwise, we're going to get a negative area. So now you might ask yourself, why didn't we do this before? Well, we implicitly did. But like here, for example, you're actually just subtracting 0. Okay. The bottom function is y equals 0. In other words, the equation of the horizontal axis. So if you wanted to call this g of x, you could, but its value would be 0 all across this horizontal axis. So technically you are subtracting that, but we don't usually bother with it because it's understood that it's 0. So instead we just integrate the top function from a to b. Okay, so in other words, what you're seeing here is simply a special case of this one, where the bottom function is the horizontal axis and therefore has a 0 across the real number line. But other than that, nothing has really changed. So, and by the way, what exactly is happening here? This is exactly what we saw when we originally introduced integrals. You're imagining that this area is a series of rectangles. And now remember, with these rectangles, the height of the rectangle depends on whether or not we're using the left endpoint or the right endpoint. Okay, so we have like x1, x2, x3, x4. The height of the curve is either, in this case, x1 or x2. Well, the way I've drawn it is x2 here, but either way, you're going to have a series of rectangles. And in this particular case, as you can see in the bottom, the height, depending on whether you've chosen the left or the right endpoint, is going to be the difference between the two, f of x I star relative to the horizontal axis, that is. In other words, g of x I is the height above the horizontal axis. F of x star is the height above, again, the horizontal axis. So the difference between the two is what's left over, this piece. And the width is just delta x. We choose that. Now you can see that if we choose a very wide delta x, the approximation will be good, but not perfect. Okay, because the shaded regions here are very different, or somewhat different than the actual area between the 2 curves. So you can imagine what's going to happen if we take the limit of this difference as the delta actually shrink. And by the way, this is what we're seeing there. This says that the area of interest is approximately equal to the sum of all these rectangles, okay? This is the height of each rectangle. Let's call this rectangle I. Now, remember, the widths are all the same. It's a constant. That's why there's no I subscript, by the way. This is the common width of all the rectangles. And so the height times the width equals the area of a rectangle. So the sum of all these rectangles, of which there are n of them, is the shaded region. But if you notice, especially on the left, those rectangles are a little too tall. And so it looks like, in fact, on the bottoms, they're a little too low too. It looks like the way this graph, the way it's written, the rectangles will be a little larger than the actual area between the curves. But if we keep increasing the number of rectangles by shrinking delta x, in the limit, as delta x goes to 0, this converges to the integral, because remember, an integral is an infinite sum of the difference between f of x and g of x. So in other words, delta x converges to dx, and the sum converges to the integral. And so what this does is it justifies this formula. Okay, so let's do a quick one. Let's look at the area between f of x is x plus 4, which is clearly a straight line, and g of x is 3 minus x over 2, also a straight line, over the interval from 1 to 4. You can see, if you measure this properly, I mean, this is clearly that blue area is a trapezoid of some kind. You could theoretically do this with geometry, but we're going to do it with our new technique. And you can see that f of x is on top within this entire interval. And by the way, if you notice, they do cross, and there comes a point when g of x is actually on top. But in the interval of interest, which is here, f of x is always the one on top. So the area will equal the integral from 1 to 4 of f of x minus g of x dx. Okay, so algebraically, that's going to be, and here you can see I've worked out all the steps. And so I dropped the parentheses, and I ended up with this expression, 3x over 2 plus 1 integrated between 1 and 4. So we can simplify that just a little bit more. Let me show you what's on the next slide. Okay, I've repeated this result here. So I've broken it up into 2 integrals, and I've moved the constant 3/2 outside. And now this will be easier to deal with. Integral of x is x squared over 2. This one will be x. Let me write it like this. Now, if you choose to do so, you can move this constant outside. And now you just have to evaluate. You do some substitutions, which I've got in the next slide. And this is where we left off. And now within the brackets, you've got for this first one, 4 squared minus 1 squared. And for the second one is simply 4 minus 1. So you've got 3/4 of 16 minus 1 plus 3. 45/4 plus 3. 57/4. That's the area between those two lines. So it's just a very simple extension of what we'd previously been doing when we were looking for areas under a curve. The difference now is that we're looking at the area between two separate functions, which you can call them curves even when they're straight lines. I mean, a line is a type of curve when you think about it, but whereas before all of our examples were based on the idea that the so-called lower function was simply the x-axis. How interesting. Now, what happens though? Now, if you notice, that was a very nice example because no matter what happens, it was something like this. In the interval of interest, f of x is always on top. What if that's not true? What if you have something like this? Okay. You know what I'm going to do? Hold on. Let me draw it a little differently. And the area of interest is between, let's say, 0 and here, let's say. And let's just say, even though I maybe didn't draw it that well, between 0 and 2, f of x is on top. And between 2 and 3, g of x is on top. Now, what do we do? Well, what we're going to do is essentially the same thing, except we're going to calculate this area and then this area and add them up. So in effect, what we're going to do is integrate from 0 to 2, f of x minus g of x. And then we'll add to that from 2 to 3, g of x minus f of x. So it's only a bit more messy. Now, of course, for every time the two switch, then we'll have to have a new integral. So here it's just once, they cross once. But if they cross twice, then we might need 3 of these, and then we might have 4. But the basic logic is always the same. So I'll tell you, why don't we save this example? By the way, these are called compound regions. And so anyway, we'll do this example. This will be our first example for our next session. And so in the next day or so, I'm posting a problem set, which is based entirely on chapter 1. And you'll have at least a week to do it. So that's what's coming up next. So next time we meet, we'll carry on with this chapter 2A. And then I'll assign the first assignment. And it'll just be everything we were doing in chapter 1. It's really a good opportunity to get some practice, because you're seeing certain examples, and that's fine. But it gives you a chance to try others and see how well you really understand it. And then if you realize that you don't know how to do them, then we can have a Zoom session, or you can send me emails. But once you start working these problems, that's when you'll really find out how well you understand this stuff. So, all right, anyway, so I guess I'll just see you next time then.